Okay, so we're going to continue with acids and bases. Take a little closer look into these conjugate acid-base pair relationships. Okay, put your head on a little bit for this one, right? Tighten screws a little bit. Get straight to work here. All right, so types of reactions can have a precipitate reaction, we have an acid-base reaction. We are continuing in these acid-base reactions, okay? So we're going to look at conjugate acid-base pair relationships. All right. If we have a strong acid, what does that mean? That means we have 100% dissociation, right? If we have a weak acid, we have less than 100% dissociation. The weaker, the lower the dissociation, right? It doesn't have anything to do with being dangerous or not dangerous. It just has to do with how much of the hydrogen ion that is present actually dissociates and goes into the solution. The more, the stronger, the less, the weaker. Strong acids have a one-way arrow. Reaction goes to completion. All right, weak acids have a two-way arrow. Equilibrium is established. Now, we will have several units on equilibrium next semester, so I'm going to try not to get too much into it here. All right, we have a two-way arrow in equilibrium, so that some reactants are present and some products are present. And we have a dynamic process, which we'll talk more about later, where reactants are constantly forming products and products are constantly forming reactants. And we have this dynamic process of going back and forth, right? Okay. Now, when we do that and we talk about acids and bases, remember we've got acids and bases over here. And we've got conjugate acids and conjugate. Let's write that in the opposite direction because they'll go together. Conjugate bases and conjugate acids. I don't know why I did that over here. Okay, such that this will be an acid conjugate base pair, and this will be an acid or base conjugate acid pair. Okay. Now, when we talk about equilibrium, I'm just going to write EQ systems have K values. Right? The K value is a ratio of the products to their exponents over the reactants. Okay, and without getting too much into this mathematically, what you can see here is that if K is greater than 1, then more products than reactants at equilibrium, because K is a ratio of products to reactants. Okay, if K is less than 1, then more reactants than products at equilibrium. And then you could infer that if K is pretty much equal to 1, about the same amounts, right? Okay. So this is important, right? For any strong acid, we have really, really large Ka values. Sometimes they're so large you don't even have Ka values. Right? They don't have Ka for acid, okay? Weak acids, they have Ka values. All right? And the higher the Ka, the greater the dissociation, the stronger. The smaller the Ka, the lesser the dissociation, the weaker. Okay? Now, it is true that we have Kas for acids, right? Value relates everything I just said to extent of dissociation. Larger Ka equals more dissociation. Simple as that. We also have Kb values for bases. I kind of think of it as the value, what do bases do? They take hydrogens. Relates to ability to, I'm going to write hold onto the hydrogen. Or take, to take and to. To take relates to ability to take and hold on to the hydrogen. You have to think about these things and just find a way to wrap your head around it. And once you do, it makes sense. Now, an acid-base pair, you need to realize, right, or conjugate acid-base pairs, this would be a conjugate acid-base pair, right? Please note that this is also a conjugate acid-base pair. However, this is not a conjugate acid-base pair. Okay, this is not a pair. I want to make sure you realize that, because a conjugate acid, I don't know, a pair, I'm just going to write a pair. A pair must be separated by only one hydrogen. And this is separated by 2. Right? Therefore, this is not a conjugate acid-base pair. Okay? So I just want you to visually see that. It's got to be separated by only one hydrogen to be considered that conjugate acid-base pair. Okay. Now let's look at our relative strengths and kind of see if we can end this here. So if I have a strong acid, then I have a weak conjugate base. So if I have a high Ka, I have a low Kb. Okay. Let's look at an example of that. Let's look at our strong acid, HCl. We need to incorporate water here. Strong, it'll go in one direction. The hydrogen, this will be my acid. He'll lose all of his hydrogens, and the water will take it. Okay, so right here, we have a very strong acid. And this is my conjugate base. Well, as we said, it's very weak. And I want you to visualize it. All right. In order to act as a base, Chloride would want to take back his hydrogen and turn into HCl. Well, by definition, HCl is strong, which means he donates all of his hydrogens. So he will always exist in solution to the greater extent than this form, right? All of this dissociates into hydrogen ions and chloride ions. So this conjugate base of a strong acid is weak. It's got no ability to take back and keep the hydrogen. And if that doesn't make sense to you, I need you to bring it up in class, okay? Because surely someone wants more of an explanation. Let's look at another one where if I have a weak acid, right, then I would have a low Ka, and that would give me a strong conjugate base, which would in turn have a relatively high Kb. So let's put a weak acid down here, like NH4, the ammonium ion, in water, right? I'm going to make that H2O. No, yeah, I am. H2O is going to give me, he's going to donate, this is going to go both ways. So some of the ammonium will dissociate and will donate their hydrogen ions to the water, but not all of them. So because this is a weak acid, hydrogen ions are not readily donated. In fact, what you want to think about in your head, this is the way I've learned to look at it, is, let's see, they're not readily donated. Ammonium would like to keep them, right? Don't put that in an answer. Think about it like that. Ammonium would like to keep its H ion, okay? And we know that because it's a weak acid. Weak acids want to keep their hydrogens. They don't want to give them away to the solution. Those are your thought processes, not your words, okay? They do not dissociate completely. Those are your words, okay? So if this is weak, okay? If this is weak, when what that means is this is strong. And what does it mean to be strong? It means it will take back and keep its H, or the H. Let's write the H. It's not his. The H. So that will push the equilibrium this way. Okay? That will push the equilibrium this way. And if we push it that way, we will have more reactants. And we will have less products. And we will have an overall K value that is less than 1. Now the K value is for the entire system. The Ka is just for the acid. The Kb is just for that acid's conjugate base, right? All right, it can be kind of confusing. It can be kind of confusing, all right? Let's put, actually I have an example. I'm gonna go to, I downloaded, I'll put it in worksheets here, and it's right here. We might look at this some in class together too. We don't want to do too much. Okay, that's actually what we just did. Okay, let's look here. Let's look here. So we've got two acids present, all right? This is an acid, which we have right here. Okay, with his Ka value is times 10 to the negative fifth. Here's another acid here, HCN, with his Ka value that goes times 10 to the negative 10th. So this is smaller Ka, therefore this is a weaker acid, right? Therefore keeps H better than other acid, right? Right? So I know that my equilibrium is going to lie over here. Now, I could have looked at that a different way. Let's look at this one here. Let's look at the Kb. Let's find our bases. Well, they're identified for us. NH3 is here. It's at -5. CO3 is a base. It's at -4. This is larger, therefore strongest base. Therefore best at taking and keeping the H, right? So if he was to take and keep the H, we would go this way. If he was to take and keep the H, we would be pushed this way. This is in fact who's going to win because his Kb is larger. So that tells me that this will not happen to an extent greater than this. Reaction will go over here. We have a K again that is greater than 1. Up here we said we'd have a K that is greater than 1. All right. Now in order to do this one, I need to know what my Ka and I would compare my Ka and my Kb. However, I happen to know this is one of the strongest bases around. Therefore, this will be a stronger base. And this will be the weaker base. So once again, he will take back his hydrogen and we will have the product favored. I say that is product favored. So in every one of those, it looks like we're product favored. Let's go ahead and name our strong acids. Let's put them down. Make sure you have them. Hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, sulfuric, first hydrogen only. We'll talk about that later. And often people include chloric, okay? If it's not one of these, it's not strong, it's weak. Strong bases, you're going to think sodium hydroxide, potassium hydroxide, lithium hydroxide. I think your group 2 hydroxides, but they get kind of wishy-washy, so I'm not going to write them there. But typically you're thinking about these guys. Maybe the magnesium. Okay. I guess you could add strontium or barium here. I don't like to do that because they get a little wishy-washy there. I don't like putting the word strong there. Okay. All this other stuff we're really not ready for yet. But I think that was good. Let's look here. Let's look here. Write the equation for the reaction of HSO3 negative with water in which it acts like an acid. Okay, so if he's going to act like an acid, he's going to lose his hydrogen. He's going to become more negatively charged from a negative to a 2 negative. The water will gain it, become positive charged. Notice my balance of charges. Over here, I'm a negative and a neutral, which makes an overall negative. Over on the other side, I'm a 2 negative and a positive, what makes an overall negative. So I have a -1 and a -1. That should always work every single time. Balance of charges. Okay. Circle the strongest acid. Okay. The value of Ka, so K is to the -7th. Well, K is less than 1, so equilibrium lies to the left. We have more reactants. Okay? So if equilibrium lies towards the left and we have more reactants, we have more of this. Okay? And we want to know, identify, circle the strongest acid. Well, there's 2 acids present. One is the reactant acid, and one is the conjugate acid. Okay, what do acids do? They give, the strongest acid gives away its H the best. I mean, you cannot put those words in your descriptions. That's what's happening up here, okay? So since we have more of this, he must have given away the best. So therefore, water here is a stronger acid than this hydrogen sulfite ion. So the answer here would be water. I told you to put your head on for this, okay? We didn't do everything. Let's do one more here. I see another good one. Write the equation for HSO3 negative with water, where it acts like, I'm gonna write H2O, where it acts like a base. Okay, H2O. So if HSO3 acts like a base, it will lose. Oh, no. To act like a base, right, is to take. So he's going to take his hydrogen back, and he's going to take it from the water, right? So here we have a base, and over here we have our base, our conjugate base. And the question is, we don't know enough to do this. Okay. We just don't have enough. I don't need to get into all this. Okay. But here we would see that equilibrium was going to lie over here. I don't want to go there. I shouldn't have done that problem. Okay. Now, a little bit of that is a little bit more than you need to know right now, but you're definitely going to need to know it all eventually. But it'll more fit into an actual unit. But right now, that will be the end of what we are talking about in terms of acids and bases. Okay? Good luck. Bring your questions. You should have them. Oh.